Okay, so good morning everyone. Let's kick this off then. Okay, so another 9 o'clock, another early start, and still quite a few that are still here. That's good. And the numbers keep going up, which is great. Right, so at the end of the last lecture, we started looking at these small signal models. And we'd finished the last lecture by looking at this, but we'd also looked at large signal models, simplified large signal models, and how we can start to apply the large signal model, and we identified the need for biasing. So we use the large signal model to bias our transistor circuit at a position where it's sort of waiting for a signal to come in. So it's sat at its sort of active point. It's called its quiescent point. Waiting for a signal to come in, and then the signal comes in and it superimposes itself on that quiescent point, and the circuit responds because it's in that linear part of the curve. And the question becomes is exactly how is it responding to that small signal? What is the actual gain for a given set of operating conditions? And a small signal model allows us to to get that quite straightforwardly. Again, allowing us to apply some linear theory to things that are non-linear. So just to recap then, what is a small signal model? A small signal model is a linearized model of a non-linear system centered around an operating point. So we position our transistor at some point on its operating curve, which remember is an exponential, and then we say, as long as we only move a small distance from that one point on that curve, we can approximate that to a straight line. And that's what we're doing. We're linearizing around a single point and just saying that as long as we don't move very, very far away from that point, we can treat it as a straight line. And depending on how nonlinear the curve is, that depends how quickly the error extends. But the curve, or our linear model, is absolutely accurate at that one point on the curve because it's a single point. So only when you start to deviate from that point that errors start to increase, and usually the errors are quite small to start with, very small deviations, and we can sort of live with that. So that's the idea. And then we started looking at this idea of well, actually we can do a superposition, but instead of superposition by just suppressing DC sources, we can actually do a superposition by splitting the problem into an AC and a DC solution. Exactly the same ideas apply. And so in the case of this transistor here, we said, well, we're going to split the analysis into two parts: the bias or quiescent part, and we gave that these capital letters to identify the fact that it's static and not moving, and then the small signal part, which we gave small letters to show that it is actually moving. So we've broken this into a static solution, and then the other part is a superimposed AC moving signal on top of that. And the total becomes a combination of the two. So we just add the two solutions together, one for the static solution and one for the AC solution. And it applies across any variable in that circuit. So that's what we're trying to do. And you can see that if we wire it up like this, then we've got a static solution here because there's no components that worry about frequency here. So as long as we have a power supply here, we will always get a current going down here. And if we get a current going down here, if it's DC, the only place it can go is into the transistor. It can't go through the capacitor because a capacitor looks like an open circuit to DC. It's just two parallel plates if you think about it, and there's no way a DC current can get through a parallel plate. Not unless the voltage gets super huge, of course. So the current has to go this way and into the transistor, and we know that if there's a current being driven into a transistor here, we get another current through here, which is beta times bigger. So this means that for no signal coming in here at all, we've got a static condition. So we've got a constant current going down here, which is defined by the value of this resistor, and we've got another constant current flowing through here, if we assume that no current can escape out of this point here, which is not connected to anything in this case, that's fine. We've got another current flowing through here, which is static and not moving. So we've got a sort of an idling current, if you like. It's not doing anything useful, but it's positioned this on on the operating curve to a place where we want it to be. Then when an AC signal comes here, it goes through the capacitor, because capacitors allow AC to pass through, and it adds itself to this signal, this node here, superposition, and we can see that this will be wobbling up and down now, and so this current through here will also be wobbling up and down, and therefore this voltage will wobble up and down because this resistor converts the current to a voltage. That's what we're aiming for. And what we'd like to know is, what's the effect, what's the gain of this signal coming in here when it comes out of here? What's the relationship between the two? So we're looking for a linearized model of our transistor that allows us to calculate the gain of our amplifier for small signals when the transistor is already biased. Right, we've biased it, so we assume that the thing's biased already, and we've biased it by looking at the large signal conditions with our simplified large signal models. So we've done half the calculation already. And our model that we're going to be developing for this transistor needs to relate an input parameter to an output parameter. And in the case of a transistor, the output is a current. The input can either be a current or a voltage. If we want to turn the output of the transistor from a current to a voltage, then we just need to put it through a resistor, and we can then pick off the voltage if we want to. Right, so that's where we got to, and this is where we now start to look at this in a little bit more detail. So there's a couple of curves here. They look a bit complicated, so we'll just look at those in a little bit. So what we're looking at is the base current, the input current to our transistor, compared with the input voltage, VBE, the base emitter voltage. So this is the input voltage, and this is the input current. And so in this case, we're controlling a voltage going in, and we will get a current as our dependent variable, if you like. So this is just the relationship between the voltage and the current going to the transistor, and we know that it looks like a diode, so it's an exponential type of curve. And what we're going to be interested in is the slope of this curve, this nonlinear curve, at any particular point. And the slope is obviously related to the exponential, and it's the differential of the exponential. If we actually then plot the tangent to the normal at any given point, we can see that we've got a straight line that just kisses the surface at zero angle. And that is the slope at one particular point where the curves actually touch. And you can see we could have a family of these straight lines if we wanted to. And we define the slope on the input side as just being 1 over r pi, because it has units of conductance. So if we want to look at a bit later, you'll see why we turn it into resistance. So we just say it's 1 over a resistance or a conductance. Then if we look at the output side of things, we've got collector current now plotted against VBE, the input voltage. And what we've now got is exactly the same curve. It's just that IC is going to be beta times bigger than IB because of this. So these are identical curves, it's just we've got a scale factor on this axis. So this is the relationship between the input of the transistor and the output of the transistor. So we've got exactly the same thing, and we've got the same slope and the same everything over here. And in this case, we call this output slope, don't worry about R at the moment, we've got this output slope which is measured, and we call that GM because it's got units of conductance, okay? And it's the slope, yeah? So it's not going through 0, 0. We're not plotting this because this is a non-linear relationship. We are saying that the resistance or the conductance here is the rate of change of current with voltage at a particular point. Okay, so this is a dynamic impedance. It's not, strictly speaking, a direct implementation of Ohm's law anymore. We're saying that this conductance is just the relationship between the rate of change of VBE and the rate of change of IC. So it's just the differential, the slope of this curve at a given point. Okay, which is effectively the impedance at that point. If we take the slope as being the impedance at any one point, you can see the impedance is varying depending on what position we are on this curve. So that's the whole point of the exercise. If we do the large signal model and put a bias place in, we're going to fix it at this point here, and therefore the impedance is going to be looking like this at that set of operating conditions. And as long as we don't move too far away from that point in our operating, then we can say that the conductance is effectively the same, hasn't moved very much. That's the concept that we're trying to get over. So in a bit more detail, this is the graph we looked at, so the input to the output, exponential function, slope at a given point. The equation of this graph is actually given by IC equals, if you remember, think back to the emitter equations that we talked about in the first couple of lectures on transistors. It's the diode equation, which is IS, which is some saturation current, leakage current in the backwards direction, multiplied by an exponential, which is related to VBE. And the slope of that is just that differentiated. So DIC over dVBE is equal to the rate of change of this curve over here. But we know that we are operating at this quiescent point. We're fixing it, are operating at this one point here, okay, whatever that might be. And so we can say under those conditions, the AC, or the small signal part, which is the same thing, is set to 0 because we're not moving. We're fixed at that point, so we're not wobbling up and down. We're just fixed at that point. We're limited to that point there. We can say that the total current, which was the sum of the DC solution and the AC solution, we're saying the AC solution at the moment is 0 because we've set it to 0 arbitrarily. So that just leaves us with the total current is equal to the static current. So it's not rocket science. We are just saying if this happens to be 0, then these two happen to be the same. And therefore, under those conditions, IC total is equal to big IC, the static. Okay, and we'll worry about this in a couple of minutes. So, in formal terms then, the total current, which is the little I and the big C, differentiated, in formal terms is that. It's just a straightforward differential, and that gives us this. And if we now again constrain it so that the AC side is 0, so that little I big C equals big I big C, we end up with this, which is very similar, except we've just changed this to the big VBE, because that's what happens when we constrain it. And if we do that, because the definition of IC is IS QVBE, if you look back a few lectures, that's the definition of it, that just becomes IC. So we end up with the slope of this curve being related to the DC component at that particular point in the curve under those conditions. So the nice thing about this is that this complicated exponential thing here boils down under those conditions to some constants Q, K and T. T is temperature, which is we assume can be constant, and some constant current, because this is the DC current that has been fixed by our large signal model for a given set of values of resistances and the type of transistor we've got. So this is basically just differentiating the exponential, but this is the key answer that says that at the operating point, whatever that operating point might be, this is the value of GM, the mutual conductance, down here. Okay, and it's linked only to the static current flowing when we've biased it. So if we want to change GM, which is, remember, our link between the input and the output, it's the slope. If we want to change that, because that's effectively the gain, all we need to do is change the bias conditions a little bit. If we change IC, which remember is our static current, which we've set by adjusting a base resistance, we can change the slope, and that effectively changes the gain of our amplifier. Right, so this is a big leap, but what it allows us to do is start to construct the tail end of our small signal model. So the relationship between the current and voltage at the output is the slope of that particular curve, which defines the output. And so what we're really saying then is the output current of our transistor is related to the input voltage, which will be over here eventually. So this is a dependent source, and the link between the two is this thing called GM, and GM, we now know, depends on whatever the static current was. So this is an AC model. This is the AC performance. Okay, but it's being defined by the DC current that always flows through the device. Okay, hopefully I'm back. Dropped out there. Okay, if someone just wants to let me know they can hear me, that'd be great. Yep, great. Okay.
We can hear you.
Thank you very much. A voice. That's really good. Okay, so hopefully you got all that. The good news is that I'm recording this locally as well, so that when I upload this, you won't know that you've dropped out, or you won't know that I've dropped out. But anyway, so just to recap to where we were, because this is quite a subtle point. I was saying that the output of this model here, this current source here, the current that goes through it is defined by whatever the input voltage variation is. So this is small VBE, so any small variations over here will result in a bigger current going up over here. And the relationship between them, between this input voltage and this output current, is this term GM, which is, we would call a constant, but we put that in inverted commas, because it's constant if the static current through the device, the IC, the big IC, is constant. So if we set a bias condition with a constant bias current, we get this constant GM, which dictates the value of the gain. Right. Hopefully that isn't too complicated. So if we look at our model, we've now defined the output end of our model. It's simply a current source that gives us a current related to a change in input voltage, VBE in this case, and the value of that is defined by this thing called GM. Okay, so even if we don't quite understand exactly what GM is, we can just say that's a constant of proportionality between this input and this output. But we haven't got anything over here at the input. At the moment, B is not defined. We haven't decided what's going on. It's an NPN, it's a PNP, it's just a question of directions of currents. It's a transistor, okay? It's all abstracted. Right, so refer this back to the base. If we've been looking at the collector current so far, we'd like to know what's going on in the base area. So we remember that IC equals beta IB under all conditions. Therefore, the input slope is just beta times smaller, if you like, than the output slope, because they're just related by this equation. So we just have to take whatever the slope was of the output curve, yeah, which was this, and divide it by 1 over beta. We're just applying this equation. So the slope of the input side becomes GM, because that's GM, over beta, and that's just G pi if we want to carry on with our definitions like that respect, where pi just refers to the input side, and conductance is just 1 over resistance. So this could be the equivalent of a resistance of the same value, of 1 over, in this case R, and we just call it R pi. So this just gives the input resistance as R pi, okay, which is 1 over conductance. That's all we're doing. It's really just two sides of the same curve. And the reason why we want this one to be a resistance is because when we put it in the model, we'd like to be able to draw a resistor. So let's do that. So given that, we can just model the input side as this resistance R pi, and this P is a pi. Okay, so that's just 1 over G pi, if you like. I'm going to call it that. So it's just called a resistance because we draw it as a resistance. That's the obvious way to do it. So this becomes our model, small signal model, for our transistor. So this is the model of a transistor that applies for AC signals in a biased circuit. And we can see that we've got an input resistance, which at this operating point is the equivalent to a resistance of value R pi. Okay, and we've also got this dependent source at the output whose value is dependent on VBE, which is the input voltage over here. So if we change this input voltage over here, we will change the output current over here. And the relationship between an input voltage and output current is most conveniently written as a conductance, GM. We could replace that with 1 over Rm if we wanted to, have VB over Rm, but it's just convenient to write it as a conductance. Okay, two sides of the same coin, there's no difference in the numbers. So this is just a convenient way of drawing a model, and this is called a hybrid pi model, for reasons lost in the midst of time, but it's got something to do with looking like a pie shape, upside down probably. And in fact, when we come to the second year, you'll find there are some other components linking this together, and it looks more like a pie then, than that pie being not an apple pie, you let a Greek pie. So that's what we're looking for. This is the fundamental thing, and it all hinges, the performance of this, the value of R pi, the value of GM, which are the only two things that are things that we have control over in this circuit, are all defined by IC, where IC is the static current set up by the bias conditions which you've calculated for a set of conditions with your large signal model. Right, so we've got large signal, calculate IC, yeah, and then when we add a small signal, the IC affects the performance by giving us these pseudo terms R pi and GM. So this, in summary, is our basic hybrid pi model. Alright, so this is something that you need to be very familiar with. It's a linearized model of a nonlinear system operating at a fixed point, and so that becomes a very powerful model for all kinds of systems. In this case, it's a transistor. We've got R pi as our input impedance, or equivalent input impedance I should say, and we've got a current source model at the output with GM and VBE. VBE is our input, GM is our constant of proportionality between the output and the input. And these two parameters, GM and R pi, are defined by these relatively simple equations. GM is equal to IC, which is a fixed value from however we've set the bias conditions up, divided by some constant, and KT over Q, and we normally define this as being 25.3 millivolts. If we take the standard value of K, which is Boltzmann's constant, and we take T, the temperature, absolute temperature, and Q, charge of an electron, I actually worked that out. It comes out to 25.3 millivolts at room temperature, and we quite often just take that as an approximation to be 25 millivolts. And R pi is then beta, and beta depends on the transistor you're using, divided by GM, which we just calculated from this, and that's linked back to this static current. So it just comes down to some sort of semi-constants that you can calculate. Right, so this now allows us to define a procedure for analysing some simple transistor circuits fully. And the procedure would be to calculate the quiescent condition, the operating point of your transistor, by setting up bias conditions and allowing yourself to then work out what the collector current is, because that's the fundamental thing that you're interested in. This allows you to then calculate the equivalent values of R pi and GM for our small signal model, and then we can use that small signal model to understand what's happening for small signals coming in. Okay. Now some of you might be asking, well, if we've got this nice linear relationship between IB and IC with beta, just IC equals beta IB, why are we messing about with this nasty exponential relationship between the voltage and the output current? That's because usually we like to have voltage facing circuits, because that's just what we're familiar with. Constant currents or currents that vary are a little bit more tricky to arrange sometimes, but if we could do that, then it would be absolutely fine, and sometimes that's a useful thing to do. So you might see in some other books and texts and things that this output parameter here is defined in terms of IB rather than VBE. So if we just remind ourselves, the model we've been looking at has this output side defined, controlled by the input voltage and this constant GM. So the current is defined by an input voltage VBE. We have a choice. We can also define it in terms of an input current if we wanted to, through here. And you will see then that the model says, well, the output current is related to the input current. So IB, a variation in IB here changes the value of this. And we have another constant of proportionality, which is quite often called HFE, and for the intents and purposes of this course that's identical to beta, but this is the commonly used expression. So when you see HFE, it actually means beta, and this goes back to well, it just means that over the years people have just not standardized their terminology depending on what they're doing, and I think Paul probably mentioned that at one of his control lectures, that there's no standardization across the world as to what letters are used for these constants. You just have to know their constants and what they mean. Okay, so we would expect this model to perform the same as the one we've just looked at, the hybrid pi model, because you can't have two models modeling the same thing giving you different answers. That's just not sensible. One of them must be wrong. So they're actually the same, and armed with a bit of linear theory and some simple knowledge of what's going on, you can show they're the same. And it's a bit like the source transformation theorem that we looked at. We say that IB times R pi is equal to VBE. So IB multiplied by R gives us VBE, which is just Ohm's law for the input side. Then we can say that GM VBE, which is the output of our hybrid pi model, must be GM R pi IB, because VBE is equal to IB R pi. You know, that's just the link between the input variables on the input side. And that must be, if this model is to hold true for the other one, the identity of beta IB over here. Okay, and then we can start to see that if that's going to be the case, then GM R pi must equal the definition of beta, and R pi was defined in our first model as being beta over GM, so that's true. So they are identical, and you can swap between them as long as you maintain this relationship, which, you know, it's up to you to do that. That's fine. So the two models are the same. They've just been transformed slightly in an abstract way to allow the maths to work, and that's how it works. So why do we prefer one model to the other? I sort of alluded to that a little bit earlier. That GM, the mutual conductance, is more fundamental than beta. This goes back to sort of device physics, so we're not going to the details of this, but just have to accept that that GM is completely predictable from a knowledge of IC and temperature, and this means that all bipolar transistors of whatever type have the same GM under the same output circuit conditions. The only thing that then changes is what does the input conditions look like, and so the value of R pi may change from device to device, but the output remains fixed. Most practical amplifier circuits are voltage driven, so we are more interested in what the voltage going in, and that will be VBE, and not so much IB, because it's usually some kind of potential divider circuit that's driving these circuits. And as a consequence of some of this stuff up here and the fundamental stuff, at higher frequencies GM stays the same, doesn't change, but beta, which is the overall gain through the transistor, does not, because of various strange capacitance effects that go on at high frequency. So it's, if possible, use this version of the hybrid pi model, and that's the one with GM-VBE. They are the same, and these other effects are still there. It's taken into account in a slightly different way. Right, anyway, don't worry about that too much. Basically, use this model of the hybrid pi circuit and you won't go too far wrong. Right, so armed with that, this knowledge that is now completely abstract in your minds, we probably want to do an example of some kind. So we probably look at this amplifier and look in a bit more detail as to how this small signal model can apply. Right, so let's do a detailed analysis of a common emitter, CE is common emitter, amplifier with base biasing. And base biasing is when the biasing comes directly only to the base. So it's coming, the biasing arrangement, as we know, comes from here, goes through here, drives a current into here. That current comes through the transistor, and that forces the transistor to pull a bigger current through here. So that's what we're getting to. We've got this blocking capacitor here and an input signal coming in. So we now know, and it's also given us a few conditions. So VCC equals 5 volts, so this is the supply voltage. CC, usually double subscripts on things imply a supply voltage. So VCC, this one is quite often called VSS. And you just have to know, but double subscripts usually imply a fixed DC voltage. Just another convention. So in this case, the supply is 5 volts. RB is 820 kilo ohms. That's this one. RC is 2.2 kilo ohms. Okay. The beta of this particular transistor is given to us as being 200. And under these conditions, normal operating conditions, we've been told that VBE is equal to 0.6 of a volt. So this is the voltage across here, 0.6 of a volt. So this is effectively, these are conditions that work. We know this because that we're otherwise a bit pointless doing the exercise. But the question is, how well does it work? So we start by determining the DC bias conditions. So if we say there's no input signal coming into this thing, Vs equals 0, there's nothing coming in here, we're only interested in this part of the circuit under those conditions. And this allows us to say, under no signal conditions, what is the status of this circuit? What's going on? What's the value of IB? What's the value of IC? And then, what's the value of V out under those conditions? And ideally, we would like, with no signal coming in, we would like this voltage here to be about halfway between this point and this point. Because if it's halfway between this point and this point, it's got a chance of going up and down and amplifying any signal that might come in. If this is at 0, for example, then it can only amplify up, and if it's pulled up to the rail down here, it can only ever come down. So usually we would like this to be sitting at around about halfway point between here and here, so it's got a chance of going in both directions. So it's biased in the middle of the conditions. So that's what we're trying to sort of achieve. So under these conditions, IB, the base current going down here, so this is applying a little bit of linear theory but implicitly, is VCC, the voltage at this point here, minus VBE, which is the voltage at this point here. So that's the difference between them, must be dropped across this resistor. And then the current must be whatever that voltage is dropped across here. If you know the voltage at both ends of the resistor, you can work out the difference. Divide that by RB, whatever that is, and that will give you a value of the current flowing through. So this is Ohm's law being applied. Now we know VCC is 5 volts because it's told us that. We know VBE under these conditions is 0.6 of a volt because it's told us that. And we know RB is 820 kilo ohms because it's told us that as well. So there's nothing that we don't know here. So we know that 5.36 microamps is now flowing into the base of this transistor. Next question is, what's the current flowing through here under those conditions? So it's going to be beta times bigger. So you can take 5.36 microamps, if you've already worked that out, multiply it by beta, which is 200, and that gives you a value of 1.07 milliamps or so. So quick sanity check, microamps sounds reasonable, milliamps, it's bigger, that's okay. If this was amps, we'd probably be in trouble, so we can just check that we've got some sensible units going on here. So we've got 1.07 milliamps flowing through here. So we know the current, which is half the battle. We just need to work out what this voltage is at this point here now. And again, we can know that this voltage is at 5 volts because that's the power supply. We've got a resistor we know the value of. We know the current flowing through this resistor, so we can work out the voltage drop across this resistor. Is VCC coming from top row? Yes, it is. Supply, this is VCC up here. Let me dare to write on it. Okay. So we've got that, and that's good. We've got current going through here. So if we know the voltage at this end is VCC, and we know the voltage, and we know the current flowing through here, which is 1.07 milliamps. If we know the voltage and the current, and we know the resistance, which we do, it's been told to us 2.2k, then we can work out the voltage at the other end. So VC equals VCC, the supply voltage at one end, take away RC times whatever the current is going through it, which is 1.07 milliamps, and RC is 2.2k, so you can work that through, comes out to 2.36 volts, so 5 minus 2.36 volts gives us 2.64 volts. So 2.64 volts is what we're looking at there. That's a 6, that's a 4, just to be clear, that's that down here. So we now know that under those conditions this voltage is sitting at 2.64 volts and doing nothing because there's no input signal coming in. So we've got a current going down here, we've got a current going down here, a baby current going down here, and they're combining down here, and the net result is we've got 2.64 volts at this point because we know the current and the voltage dropped across here. Okay, so that's our bias conditions. And remember, for the bias conditions, the thing we were really interested in was IC, because that then maps into our small signal model. And exactly how that maps in, we can see now. So what we do is we now say, okay, we've got our bias conditions, we've got our static conditions, we now need our AC conditions. We now revert to our AC model, which we spent some time developing, which is this. So this is our model of a transistor. Just here for information, so we know we've got R pi and we've got GM VBE, and we know that GM is defined by this equation, and we also know now that we've calculated IC, the static conditions, to be 1.07 milliamps, and we've got KT over Q we know is, if you put the numbers in, it comes out to 25.3 millivolts, but 25 will be fine. Do that sum and you end up with 43 millisiemens. So now we've got a value for GM, a fixed value for the condition where IC equals 1.07. The definition of R pi is beta over GM. We've just calculated GM, it's 43 millisiemens. We know beta is 200, and so we can calculate the equivalent input impedance of being 4.65 kilo ohms. So now we know what this is and we know what GM is. We've got everything that is undefined about this model now defined for our particular set of conditions. Now we replace the transistor in our circuit here with our hybrid pi model. So all we've done is we've taken out the transistor with the 3 connections and we've dropped in our hybrid pi model of the transistor as a starting point. Okay, so that's a start. But also, because we're operating an AC superposition, we suppress the other sources in the circuit, and the other source is VCC up here, the power supply. Because you imagine there's a, let's get adventurous with this pen. We would have a battery across here of VCC. Okay, those are C's, VCC. So if we want to suppress this DC source because we're only interested in this AC source, we replace this with a short circuit. Okay, and this is the short circuit as drawn in. So that's what we're doing. We suppress the short circuit. We suppress the voltage source with a short circuit and draw it like that. And this is a little loop to show they're not connected. Okay, so that's just a wire going over the top. So we've got that, and that's starting to look a bit messy. So what we should do is probably redraw that, and we'll redraw that in a minute. So I've explained why we've shorted this. So we redraw the circuit. This is what we had originally with our short-circuited power supply here. If we redraw that, you can see that this point and this point are the same voltage, so we can always sort of just fold these resistors over on themselves. It just folds back on itself. If just you do a bit of visualization, so you redraw that. So this point is at the same potential as this point, so this resistor can be drawn in parallel with R pi. Yeah. So I think it's sort of obvious. Likewise, RC is in parallel with GM-VBE because this point here is connected to this point here. So we can redraw this in this form. We've got RB in parallel with RPi. The source of our AC source, and remember we don't suppress those because we can have them both going because they're linked, they're dependent sources. And when we got RC in parallel with that. So this is what, if you were an AC signal coming in here, this is the circuit you would actually see. Okay, so if you imagine yourself as being the AC signal, this is what you see as a signal. And you can see it's changed in its form quite a lot from what you'd physically look at. So we're starting to abstract these things a bit. So this is just for analysis purposes. Why is there an extra capacitor C2? Okay, a good question. And it's because I'm not being completely consistent, I suppose. If we go back to here. The thing that I haven't mentioned is that we've blocked the input here for the DC conditions. We also don't want DC conditions to change at the output either, because IC is very important. And if we didn't have a blocking capacitor on the output when it goes on to the next part of the circuit, we potentially would lose some of our IC out of here if we didn't have a blocking capacitor. So what we've done is we've effectively isolated both ends of our circuit with capacitances, so that this can be treated as a DC block. An AC signal will not see these capacitances and will just filter all the way through and out the other end. So it's an output block. It's operating as the same as the input side. Okay, hopefully that explains that. So we're always going to have them, but it's not fundamental to the analysis of this circuit, because we haven't really looked at what the output is doing at the moment. So we're really interested in this part of the circuit. What goes on at the output at the moment is undefined, so we're not worried about that at the moment. But good question, thank you. So given that this is the AC solution, and we know that at AC capacitors are short circuits, because that's what they're there for, they're to block DC and to allow AC through. Under the conditions of AC, this capacitor can be considered to be short circuit, so we can replace it with a short circuit just to aid us in the drawing. So we've taken the capacitor that was here, and we've just said under AC conditions it looks like a short circuit, so under AC conditions we may as well not draw it, as long as we accept that this model only applies under AC conditions. And so the second capacitor that caused Mr. Shub so much trouble has now disappeared anyway, but only for the analysis. It's not, we haven't really got rid of it. Hang on, someone's trying to call me. We'll have to suffer that for a minute or two. So right, so what have we got here? So this is the circuit now that we can analyse for the AC conditions. And the AC conditions allow us to analyse this, and this is starting to look like loops and starting to look like meshes and things like that. So we can start to apply our linear theory to this circuit to work out what's going on for AC signals going through the transistor, having calculated all these bias conditions and absorbed them in to these circuit parameters. And we can almost do that by inspection in many ways. We can look at the output, which is what we're interested in, and we can say that Vout is just equal to minus GM VBE RC, because we've got GM VBE as the current flowing through RC, and this end is going to be more positive than this end, so it's just a negative voltage here. So V0 is going to be effectively 0 minus whatever the voltage drop is across this resistance here, which we know we can calculate now because we know the current through it and we know its value of resistance. So Vout is equal to minus GM VBE RC. And now we've got a relationship between VBE and Vout, which is an input parameter, but it's not the input parameter. VBE is the voltage across here, okay, because that's where it is, VB and E, and VS is the input voltage. Now, so we look back to see what is the relationship between VS and VBE, because that's effectively what we're looking for. And in this case, it's obvious that the value of VS, which is the voltage across here, is equal to the value of VBE, because it's just a couple of parallel resistors. So we can just replace VBE with VS in this case, and then we can rearrange this V out equals minus GM VS RC to be V out over VS is equal to minus GM RC. This is just that rearranged, and V out over VS, which is the output voltage divided by the input voltage, is the transfer function, if you like, or the gain of this circuit. So we know that if we put a value of 1 volt in here, for example, we will get a signal out of here that is GM RC bigger or smaller, depending on the values, times VS. In this case, if we have a value of whatever it was 2.2k I think for RC here, and we calculate a value of GM, which I can't remember what it was, but we can look back and see that, put the numbers in for this, and it comes out at a value of 94.6. Okay, so we've got a gain of a relationship of V out over VS, in this case of 94.6 under those operating conditions. So put in 1 volt, if you could put in 1 volt, you would get 94.6 volts out if your power supply was big enough. Okay, if your power supply is only 5 volts, which is in this case, you wouldn't get that out, you just get some horrible distortion. Okay, so likewise, put 1 microvolt in, you'll get 94.6 microvolts out, so it's about 100 times bigger. And we've got this minus sign. And what does the minus sign mean? What does it mean when it means it's 94 times bigger but negative? What it means is, remember this is for AC, so what we've got is an AC signal coming in, looking like that. And it's symmetric, I haven't drawn it very well. So the negative means that we've just got a phase shift of 180 degrees or so. So if I can try and sketch that, then that means that the output will go down much bigger and go up much bigger and then go down much bigger. So this has gone up, so positive input voltage leads to a negative output voltage that's 100 times bigger in magnitude. Okay, well, I think that explains it quite nicely. So that's quite a neat way of working out what's going on in your system for AC, and we've done quite a lot of abstract stuff there. We've worked out the bias conditions by using a large signal model to work out what the value of the slope is for the transfer characteristic. We've simplified that into this term called GM here as a term, so that varies with the bias current, but the bias current is normally fixed. This type of circuit is a superposition type analysis or partial superposition type analysis for an AC signal coming in with a dependent source, and it becomes very trivial to analyze this basic circuit to allow us to get an absolute value for the transfer characteristic of this amplifier under those operating conditions. Did we make any assumptions when removing the capacitors? Yes, we did. We assumed that they were short circuit at the signal frequency. This is AC, remember? So as this is AC, then any capacitor that we have here becomes a short circuit. Okay, if this was a DC source, we'd have to put the capacitors back in because they'd be important at that point because they block. But we're saying that because we're operating at a frequency where we're assuming this capacitance looks like a short circuit, we can, for the purposes of analysis only, they're not really removed, they're just not appear to be not there as far as the signal is concerned. It just makes it easier to simplify the circuit. Okay, we assumed low impedance at this frequency. Yes, we did. We're assuming, in fact, we're assuming more than low impedance. We're assuming short circuit because we're assuming everything's ideal. You know, at some point, our next lecture, we'll be looking at this capacitor in a bit more detail and saying at what frequency does it become a short circuit, and at what frequency is it a block, and where's the transition between the two. Okay, so that's to come. But at the moment, let's just assume that we can assume that they are a short circuit, and then it just allows us to draw this simpler form of the circuit for analysis purposes. Okay, is that clear? Very well. Thank you. Okay, so I was saying that's a yes, and no one's shouting no, so that's a good thing. So okay, so go back and reflect on these notes, and at the next lecture we will go a little bit further, and as I say, at some point we'll be looking at the value of this capacitance and working out when it becomes significant, and that builds on stuff that you did with I think Dan and Neil last semester, but we'll go over that again as well. Okay, so thanks for your attention. Hope that was okay. As I say, I'll upload the full recording, so the dropout will miraculously disappear, hopefully. I'll see you next week. Okay, bye for now.